afternoon, students. I hope so far you have been with me. I hope so far you have been able to follow everything, because we are taking it very slow. We're not rushing this. We are making sure that we understand everything, right? I could have just come and told you the formulas and you would have been able to somewhat solve the problems, but that's not what our goal is, right? We are taking it slow. We are understanding every single formula, every single derivation, where it's coming from, how are we actually making sure that we're counting all the cases, and how to apply the formula, as well as how to identify when the formula might not be enough and we actually have to make sure that maybe the exceptions are taken care of. Like we saw in the last class, at the very end, the last problem, we saw that we cannot just memorize a formula and apply it. We actually have to see when we can apply it and when we cannot. But the one thing that will always work is understanding where the formulas are coming from and applying that derivation directly, counting all the cases one by one, and that is how you can make sure that you get the right answer every single time. Now, moving on, today we are actually doing another kind of problem. As you can see in the title or behind me, we are just discussing one kind of problem, but it's very important when we actually have to choose at least one object. We are choosing some objects, but we have to choose at least one under different conditions and different scenarios. We're going to see this kind of problem one by one, and a very important application of this kind of problem is when we have to count the number of divisors of any natural number. So let's start. If there is any doubt, feel free to ask in the chat. Who will be teaching us RMO? I saw this question last time as well, and I don't know what exactly your problem, what exactly your question is, in the sense that are you wondering about YouTube, or are you wondering about the classes, the batch that is running on Unacademy? So different teachers, a mix of teachers will be there for you. I am here. I'm not a full-time IOQM teacher. I will keep making appearances on this channel, but I'm mainly a JEE educator. But because Combinatorics and Combinatorics for JEE and Combinatorics for IOQM is very similar, so that is why I thought I can take this up for you guys, because this is one of my favorite topics. This is something that I would love to teach. This is something I feel I can teach you well, because I have been good at it. I know how to make sure that every case is counted, which is why I'm telling you my thought process behind every single question, how to actually make sure that you are counting every single case. Okay, but a mix of teachers are going to be teaching you for RMO, for IOQM, just like how it's been. But if you're wondering about the batch, then that is a separate question. Okay, let's start. So what exactly do we mean when we say we have to select at least one object? Let's look at an example here. We have a bunch of fruits. Okay, we have a fruit basket where there is one banana, one mango, one apple, one pear and one orange. So we have 5 different fruits, one of each, in our basket, as you can see. Now we have to select at least one. We can select any number of objects out of these, any number of fruits out of these, but we have to select at least one. We have to eat at least one fruit, but it's up to us that we can select more than one, maybe 2 of these or 3 of these or 4 of these. Now you might make cases, right? Like maybe we take 1. That is one case. So selecting 1 out of these 5, 5C1, or we select 2, 5C2, or we select 3, or we select 4, or we select all 5. These are all the cases. Now if this number were higher, this would have been a lot of calculations, right? If there were more than 5 fruits here, if there were more than 5 objects, then it would have been really large calculations, right? We don't want to get into that. So let's take a look at this problem from another angle. We have solved, by the way, we have solved this kind of a problem where in the first class, in the very first class, when we were thinking about selecting one or more options in a multi-correct problem. Do you remember? How did we solve that? We had a problem that we have to answer a multi-correct question. Now, we can either select one out of those, or 2 out of those, or 3 out of those, or all 4. We can mark all 4, we can mark 3 of those, we can mark any 2 of those, or we can mark any one of those, but we have to mark one. It's a very similar problem. Even in that case, we had to select at least one option out of the 4 options. Now, just applying that same method here, we have an option of selecting the banana or not selecting the banana. So we may select it or we may not select it. Same for mango, we may select it or we may not select it. So we have 2 options for each of these fruits, right? 2 options for this, then 2 options for this, then 2 options for this, and these are not or situation, these are and situations, so we multiply all of this, right? Either we select this or we don't select this, and either we select this or we don't select this. So like this we multiply, which means we get 2 raised to power 5. But just like in that problem, we are counting one case when all of them are not selected, right? One such case would be we don't select banana, we don't select the mango, we don't select the apple, we don't select the pear, and we don't select the orange. We don't select any of these. That is also counted in this 2 raised to power 5. But we have to select at least one fruit. So that means we will just exclude that case, we will just ignore that case, and the rest will be fine, right? In all other cases, in all the rest, so what is this? 2 raised to power 5, 32. Out of those 32 cases, only one case is there where we don't select any of these. The rest 31 cases are making sure that we are selecting at least one, and we are counting all the possible scenarios where we select maybe apple and pear and nothing else. We're counting that case as well. So we're counting all possible combinations. So we just have to subtract one where we don't select any one of them, and the rest will be fine. So what is the total answer? 31. Okay. Old information, right? Just revising that same thing. So if we have 5 distinct objects, then we have to select at least one. How do we do it? 2 raised to power 5 minus 1. Even in that case, even in that problem, how are we counting all the possible number of cases? 2 raised to power 4, because there were 4 options, minus 1, because we have to remove that case when we are not marking any of those 4 options. So 15 was the answer back then, if you all remember. Now, what if we have multiple of one type of fruit? Let's assume all mangoes are identical. Okay, so let's say we have 3 mangoes, 4 apples and 5 bananas. Okay, we have 5 bananas, 4 apples and 3 mangoes. They are identical to each other. All 4 apples are identical. Okay, so now we have to select at least one fruit. How do we approach this problem? What we're going to do is, there are 3 mangoes, right? Just look at the mango basket, okay, for now. Forget about apples and bananas. Now, we can either take 0 mango, or we can take 1 mango, or we can take 2 mangoes, or we can take 3 mangoes, right? So, in total, we have 4 options now. Earlier we had, if we look at this in the same way, for this mango, we had either we took 0 mango or we took 1 mango, and that's it. So number of mangoes available plus 1, that was the number of cases we could make, right? Number of mangoes plus 1 for this case when we are not taking any mango. So just like this, 3 plus 1. So we have 4 options, 4 number of cases. Just like that, even here we can take 0, 1. We have 4 apples. So 0, 1, 2, 3, 4. We can take any number of these because they are identical. We don't have to choose. Now, but this is something very important. This is a very basic thing that students get confused over. If we are taking this case, when we are choosing 1 apple out of those 4, now it's not going to be 4C1. Why? Because all 4 are identical. It is 1 case. We won't have to take 4 cases that either we choose the first apple or the second apple or the third apple or the fourth apple. No, because they're all identical, so we're counting that as 1 case. Okay, so be very careful with that. Now that means we have 5 options for the apples, and just like that we have 5 bananas, so we have 5 plus 1, 6 options for the bananas. So we have 4 options for mangoes, 5 options for apples, 6 options for bananas. Total how many options? 4 into 5, 20 into 6, 120. But just like before, it is possible that we take 0 mango and 0 apple and 0 banana. That case is also being counted here. So we have to remove that one case. So we'll just do minus 1, and the final answer is 119. Alright, because there is at least one fruit. If that condition was not there, if the question was that how many ways of choosing, even if you don't choose any, that is also counted, right? That case is also counted, then the answer would have been 120. But if we have to select at least one, then we have to remove the case when none of these are being chosen. So the formula, let's discuss the formula. How did we get in? Like, we understood the derivation for the formula. Now let's just formalize it. So if we have n distinct objects, so for each of them we have 2 options. Either we take them or we don't take them. So 2 raised to power n minus 1 for that one case when we don't select any one of them, right? If we have p objects of one kind, q objects of second kind, and r objects of third kind, okay, we total have p plus q plus r objects, and out of that p are of one kind, q are of second kind, and r are of third kind. Then what was the answer? We have p plus 1 options for the first kind, q plus 1 for the second kind, r plus 1 for the third kind, and we have to remove that one case when none of them is being chosen, so minus 1. Now let's combine the two. Now what if we have p objects of one kind, q objects of second kind, and the rest are distinct. We in total had n objects, and we have to select at least one. Okay, so we have p of one kind, q of second kind, and remaining n minus p minus q, which are all distinct. So for the p identical objects, we have p plus 1 options. For the q identical objects, we have q plus 1 options, and for the remaining n minus p minus q, we have 2 options for each of them. So 2 raised to power n minus p minus q, and out of all these cases we have to remove that one case when none of them is being chosen. Now bacha, another way of looking at it is, please, it's my humble request to all of you, do not ever memorize a formula. Understand where we get it from and With practice, you'll immediately see, oh, I remember I've practiced it enough that this is 2 raised to power n minus 1. But do not just memorize the formula, always understand where it's coming from. So, let's say we had P objects of one kind and then Q objects of second kind, and we said the rest were n minus p minus q were all distinct. So 1, what color is left? Like this, let's say. So these are n minus p minus q, because in total we have n objects. Now we have p identical objects. So out of these we have how many options of choosing? 0, 1, 2, 3, 4 up to p. So p plus 1. From here, just like this, we have q plus 1. Then for this one, just this one object, there's exactly one object of this kind. So just like here, p plus 1 option, 0, 1, 2 up to p, here that p is 1, 0, 1, and that's it. The list ended because p was 1. There's exactly one object of this kind. Here there were p objects of this kind, so p plus 1. Here there's one object of this kind, so 1 plus 1, 2. Similarly, 2 for this, 2 for this, 2 for this, 2 and 2. So that is where we are getting this. It's not a different problem, it's exactly the same problem. Here we had p which was greater than 1, here p was equal to 1. We're still doing p plus 1, 1 plus 1, 2. So now we can just combine this, because how many times are we writing? 2 n minus p minus q times. So this becomes 2 raised to power n minus p minus q. So we combine all of these and then remove that one case when none of them is being chosen. Okay. Any doubts? Now, this is the problem that we did in the first class, if you all remember. We have 10 bulbs which can be switched on independently, right? They have 10 independent switches. It doesn't matter which has been turned on already. We can turn it on and off without, irrespective of the other bulbs. Now, in how many ways can the room be illuminated? Now, we have two options for each of those 10 bulbs, right? We have two options, on or off, on or off, on or off for each of those 10. So 2 raised to power 10 options. But this also has one such case when all of them are off. And in that case, the room is not illuminated, the room is dark. We had to illuminate the room, so we will remove that one case where all the bulbs are switched off. And that is our final answer, 1023. Okay, so this is how you can do it. Very logically, do not memorize the formulas, understand, and you will never get any question wrong. Okay. Now, a very important application is whenever we have to count the number of divisors of a natural number. In that case, it is a very similar problem. Let me show you how. Let's say we have a natural number n and we have its prime factorization. Prime factorization, which means all these p1, p2, p3 up to pk are distinct prime numbers, not composite numbers. They have to be prime numbers and they have to be distinct. That is how we write a number's prime factorization, right? And they each will have some exponent in the expansion. right? For example, if we are doing it for 24, then it will be 2 raised to power 3 into 3, and which means the exponent for 3 is, the power of 3 is 1. So they are all distinct prime numbers. P1 is 2, P2 is 3. We're not going to write 4 or 8, 6, any such number because they are composite. We have to write the prime numbers. That is how we write any numbers prime factorization. Now, if we need to calculate the number of divisors of 24. What are the divisors of 24? It's 1. 1 also divides 24. Then 2 divides 24. 3, 4, 6, 8, 12 and 24. Now 24 is a small number. We can calculate the number of divisors. 1, 2, 3, 4, 5, 6, 7, 8. In total we have 8 divisors. But for any number, if we have its prime factorization, how can we calculate the number of divisors? Just like before, our new problem is, out of these, we have to select any divisor, right? Any prime number. Now, for this, we have 3 2's, right? This means we have 3 2's and this means we have 1 3. So, for this, we have 3 2's. So, we have 4 options. We can either select 0 2's or 1 2's or 2 2's or 3 2's, right? We can either select 0 2's or 1 2's or 2 2's or 3 2's. Just for this one prime number, there are 3 plus 1 options. Where is this 3 coming from? From the power of that prime number. Then for 3, we again, just like before, we have, this is 1. So we either have option for selecting 0 3's or 1 3. Right? So that means we have 4 options for selecting 2's, including not selecting any, and 2 options for selecting 3. So in total, how many options of making a divisor is there? 4 into 2, 8, which is what we were getting. Now we're not subtracting 1. Why? Because what is that case when we do not select any of them? We select 0 for here, 0 for here, we get 1, right? 1 would be the divisor. If we are saying that we are including 1 as the divisor, then we are not going to subtract 1. If we were not including 1, then we would have to subtract that case when we are not selecting any of these prime numbers. So, bacha, I hope this is clear that as we select a bunch of 2's, a bunch of 3's, a bunch of these prime numbers, we are making a new divisor, right? Each of those divisors can be written as product of some of these prime numbers. We are just seeing how many cases can be there, how many divisors we can make, how many cases of choosing some prime numbers can be there. So, in general, what will be the formula? Alpha 1 plus 1 options for P1, alpha 2 plus 1 options for P2, alpha 3 plus 1 options for P3, and like that, alpha k plus 1 options for Pk. If the power is 1, then 1 plus 1, 2. Alright. Now, if we are not including 1 and n, we're not counting 1, we're not counting the natural number itself. Other than those two, we are counting all of them. So, out of the total, we will just subtract 2 and we'll get our answer, right? The number of divisors, the total number of divisors stays the same. We'll just subtract 2 when all of them were taken, that is n. When none of them was taken, 1. So, in that case, we would get 1 and n, and we'll just subtract those 2 cases. The other cases are fine. Now, if we need to find the sum of all these divisors, what is the sum of all divisors of 24? 1 plus 2 plus 3 plus 4 plus 6 plus 8 plus 12 plus 24. What's the sum? 3, 6, 10, 16, 24, 36 and 60. We'll come to questions. We have to discuss the theory before we get into the questions part. Don't be impatient. Listen to whatever we are discussing. Even if you think you know everything, there might still be something that you learn, something new that you learn today. Do not ever be that overconfident. A good student is always paying attention to their teachers. That is how you differentiate from a good student versus an average student. So do not ever be impatient. Always listen to your teachers. There could always be something new, a new angle of looking at things. Every time you study something, even if you're repeating something you already knew, even then there could be some new angle, a new perspective that you might yourself gain. So just be patient. Okay, so the sum of all the divisors is 60. This was anyway very long. We had only 8 divisors and we had to calculate the entire sum, and this was a lot of work. Now what if we had an even larger number? In that case, we'll just count all the possible cases. For 24, we had 2 raised to power 3 into 3 raised to power 1. So for 2, we had either an option of selecting 0 or 1 or 2 or 3, and for 3 we had this. Now if you expand all of this, let's expand this product, then we get 2 raised to power 0, 3 raised to power 0 plus 2 raised to power 0, 3 raised to power 1, 2 raised to power 1, 3 raised to power 0, 2 raised to power 1, 3 raised to power 1, 2 raised to power 2, 3 raised to power 0, 2 raised to power 2, 3 raised to power 1, 2 raised to power 3, 3 raised to power 0, 2 raised to power 3, 3 raised to power 1. What are all of these? These are all the possible divisors and we are trying to find the sum, which is why we express them as these products. Okay, so if you want to check, this is 1 plus 3 plus 2 plus 6 plus 4 plus 12 plus 8 plus 24. This is nothing but all the divisors and we are finding the sum. So if we just find this sum, which is easier because we have to find the individual brackets and just multiply instead of adding all of these numbers, right? Now, so to generalize, we have p1 raised to power 0 plus p1 raised to power 1 plus p1 raised to power 2 up to alpha 1, and like that for each of these prime numbers we'll do that. But now it still seems like a lot of work, but if you students know what a GP is, this is each individual bracket is a GP with the first term as 1 and common ratio as P1 and number of terms is alpha 1 plus 1. So like that we can form a GP of every single bracket. For each of them, the first term will be 1, the common ratio will be that prime number, and the number of terms will be power plus 1. So what is the sum of a GP? A r raised to power n minus 1 divided by r minus 1, right, where a is the first term, r is the common ratio, n is the total number of terms. So in this case, if we have to calculate the entire sum, it will be a is 1 for all of them, p1 raised to power alpha 1 plus 1 minus 1 by p1 minus 1 into p2 raised to power alpha 2 plus 1 minus 1 by p2 minus 1 into p3 raised to power alpha 3 plus 1 minus 1 by p3 minus 1 and so on. So if you want to verify, let's verify for 24. We have this GP. So what is this? 1 into R2. How many terms do we have? 3 plus 1, 4, minus 1 by 2 minus 1. And similarly for the other bracket, what's the first term? 1. What's the common ratio? 3. How many terms? 1 plus 1, 2, minus 1 by 3 minus 1. So if we just simplify this, 16 minus 1, 15 by 1 into 9 minus 1, 8 by 3 minus 1, 2. So we get 15 into 4, 60, same as before. Now this is definitely easier, this is definitely simpler, this is definitely faster. Okay. So one last topic before we get into the questions. Now, but bache, for all the students who were asking for questions, trust me, these are also questions. These are not something that we are studying just like that. These are also problems, but instead of fixed number, we have a variable instead of the number. It's still a problem. You still see such questions, right? When we do not have a specific number, we have a generic formula, a generic expression. Okay, so one last topic, number of ways in which n can be resolved as a product of two factors. We have n, the same as before, that is its prime factorization. Now we have to resolve it into two factors. What does that mean? For 24, it can be either 1 into 24 or 2 into 12 or 3 into 8 or 4 into 6, and that's it, right? 8 into 3, which has already been taken, 12 into 2 already been taken, 24 into 1 already been taken. So what exactly did we do here? We split them into pairs, correct? We split them into pairs. So 1 pair, 2 pair, 3 pairs, 4 pairs. We had total 8 factors, correct? We had total 8 factors. That means there can be 4 pairs in those 8 factors. So if the total number of factors is even, we can just divide it by 2. But what if the total number of terms is odd? When can that happen? Let's take a look. The total number of terms here is, the total number of divisors here is alpha 1 plus 1, alpha 2 plus 1, alpha 3 plus 1, alpha k plus 1. If any single one of them is odd, then that term odd plus 1 will be even and the final product will be even. The number of divisors will be even and we can just divide it by 2, right? If any of these powers is odd, then there will be even number of factors. But if all of them are even, if all alpha 1, alpha 2, alpha 3, alpha k are even, in that case, this will be odd, even plus 1, odd, even plus 1, odd, even plus 1, odd, even plus 1, odd. All of them will be odd and the final product will be odd, which means the total number of divisors will be odd. When does that happen? If all of them are even, let's say n is 2 raised to power 4, 5 raised to power 2, 7 raised to power 4 and 11 raised to power 2. We have all even powers. In that case, we can do 2 raised to power 2, 5 raised to power 1, 7 raised to power 2, 11 raised to power 1, whole raised to power 2. That means n is a perfect square, right? If all the powers are even, then we can do this to the prime factorization, which means n is a perfect square, correct? So if n is a perfect square, in that case the number of divisors will be odd, but if n is not a perfect square, then the number of divisors will be even. So If n is not a perfect square, then the number of divisors is even and we can just divide it by 2. We can just multiply the entire number of divisors by half. But if n is a perfect square, then what is happening? Then we are having odd number of divisors. Why are we having odd number of divisors? Let's see. Let's make it simple. Let's make it 100. Okay. So 100 is equal to 2 raised to power 2, 5 raised to power 2. It's a perfect square clearly. 2 into 5 whole raised to power 2, 10 raised to power 2. So 100 is a perfect square. Now what are the divisors? The divisors are 1, 100, 2, 50, 4, 25 and 5, 20. How many divisors in total do we have? 3 into 3, 2 plus 1, 3, 2 plus 1, 3, 9. So we have taken 1, 2, 3, 4, 5, 6, 7, 8. We have taken 8 of them. What is remaining? 10. Now to make the pair, we have to count 10 twice. But while counting the number of divisors, we only took 10 once, right? So the total number of divisors for 100 was 3 into 3, 9. Which 9? 1, 100, 2, 50, 4, 25, 5, 20 and 10. These are all the 9 divisors. But now we need to form the pairs. So we need to add 1, 10 again. The root of this perfect square, the square root of this perfect square, we need to add this one term again. And now we can split all of these in 2 pairs by dividing it by 2. So if we just add 1 here, we get 10 and then we divide it by 2. So we get 5, right? So 5 is the number of pairs we can get for this particular natural number. How did we get to this? By adding 1 to the total number of divisors and then dividing it by 2. So we add 1 to the total number of divisors and then divide it by 2. So this is how you get the number of pairs, the number of ways in which we can divide the divisors into products. Alright, now let's look at a problem. So we have n is equal to 2700 and we have to find certain things. We have to find total number of divisors, number of divisors divisible by 15 but not by 4, sum of divisors and sum of even divisors, like that. So we'll look at this one by one, but first of all we have to find its prime factorization. Without doing that, we cannot proceed. So what's the prime factorization? I'm not asking for the answer, I'm sure you can do it, but let's discuss this step by step. Again, maybe you might learn something, so answer. What is the prime factorization of 2700? Yes, bache, we will also cover pigeonhole principle. Thank you so much. 3 raised to power 3, 2 raised to power 2, 5 raised to power 2. That is correct because this is 27 into 100. So 2 raised to power 2, 3 raised to power 3 and 5 raised to power 2. 27 into 100. We now have the prime factorization, right? So we have 2 2's, 3 3's and 2 5's. We have to count the total number of divisors. Total number of divisors, this is simple. We have 3 options. We have 2 2s, so we have 3 options for 2, 4 options, 3 plus 1, 4 options for 3, and 3 options for 5, 2 plus 1, 3. So in total we have 3 into 4 into 3, that is 36. Total number of divisors. When nothing else is mentioned, then we are also counting 1, we are also counting the number itself. So total number of divisors comes out to be 36. Now let's take a look at the next problem. We applied a condition to our problem. Total number of divisors that are divisible by 15 but not by 4. What are we doing in that case? We are making sure that at least 15 is there. At least 1 3 and 1 5. 15 is what? 3 into 5. So at least 1 3 and 1 5 should be there in our divisors. Then we are making sure that it is divisible by 15. But not by 4. What does that mean? No 2 2's should be there. This is 2 square. So 2 square should not be there as soon as we add 2 square. For example, let's say we have 2 square into 3 into 5. What is this? 4 into 3, 12 into 5, 60. In that case, 60 is divisible by 4, but it is also divisible by 4. 60 is divisible by 15, but also divisible by 4, which is not what we want. Also, if we do not have at least 1 and at least 1 3 and 1 5, then also we will not have a number which is divisible by 15. So we have to make sure that we at least take 1 3. That means now we have how many options? We can either take 1 3 or 2 3's or 3 3's. At least 1. Here as well, we have to take at least 1. We can take 1, we can take more, that is also fine. But we have to take at least 1. 5 raised to power 0 is not an option. As soon as we do not take a 5, then it is not possible that we get a number which is divisible by 15. But here 2 raised to power 2 should not be there. No 2 2's should be there. 0 2's, that is okay. 1 2, that is also okay. It will only be an even number, but it won't be divisible by 4. But as soon as we take both the 2's, then it will be divisible by 4. So that means in total we have 2 options for 2, 3 options for 3 and 2 options for 5. So in total 12 possible divisors can be made that are divisible by 15 but not by 4. Okay, so this is how very logically you will approach this problem. You will not memorize anything. You just have to be very careful while counting the number of divisors. What's the next problem? We have to count the total sum of all divisors. So 2 raised to power 0 plus 2 raised to power 1 plus 2 raised to power 2, 3 raised to power 0 plus 3 raised to power 1 plus 3 raised to power 2 plus 3 raised to power 3, and 5 raised to power 0 plus 5 raised to power 1 plus 5 raised to power 2. Right? This is how we are counting all the possible divisors. Now these are individual GPs. All first terms are 1. So how many terms? 2 plus 1 3 minus 1 by 2 minus 1. Common ratio 3, how many terms? 3 plus 1 4 minus 1 divided by 3 minus 1. Common ratio 5, how many terms? 2 plus 1 3 divided by common ratio minus 1. So we will simplify this. 8 minus 1 7 by 1. 81 minus 1 80 by 2. 5 raised to power 3, that is 125 minus 1, 124 by 4. So we just simplify this, and what is the final answer that we are getting? 7 into 31, that is 217. 217 into 4, that is 8680. Is that what we are getting? Right? 8680, that is correct. So this is how we will calculate the sum using sum of a GP. Okay, because if we count this individually, it will be a lot more work, but using GP it becomes easier, but it's up to you. If you do not know GP yet, then you can just simplify all of this. 1 plus 2 plus 4, 1 plus 3 plus 9 plus 27, 1 plus 5 plus 25. So here we will get 7, here we will get 40, here we will get 31. And we will get the same answers, we will get the final same solution. Okay, just a different method. It depends on you, whichever you find more comfortable, whichever can make sure that you get the right answer and you don't make a mistake. Alright, so this is how you calculate the sum of all possible divisors of any natural number. Now, we need to find the sum of all even divisors. Even divisors, that means at least 1, 2 should be there. 2 raised to power 0 is not an option now, right? 2 raised to power 0 is not an option. 2 raised to power 1. As soon as we add at least 1, 2, it becomes even and then it's fine. But if we do not take any 2, then it's an odd number and that is not what we are considering here. So now the problem becomes 2 raised to power 1, 2 raised to power 2. The others will remain the same because there is no restriction for the other numbers. We can take as many 3s as we want, as many 5s as we want. All we need to do is take at least 1, 2 to make sure that we are counting only the even divisors, right? That means now we knew this product, even if you calculate 1 plus 3 plus 9 plus 27 or you use the GP formula, you will get the same answer as before, 40, same answer as before, 31. But here instead of 7 you will get 6. So either you take 2 plus 4, 6, or you can take the GP formula again in case there were larger numbers involved. Then first term now is 2, common ratio is again 2, number of terms 2 minus 1 by 2 minus 1. So this comes out to be 2 into 4 minus 1, 3 by 1, 6. So, or you can directly do 2 plus 4, 6. So whichever way you feel comfortable in, you will get the same answer, which is 7440. Now how I can check is, earlier it was 7 into this, now it's 6 into this. So that means one smaller multiple of 1240. So I'll just subtract 1240 from this. That is how you can be smart with your calculations. So 7440. Alright. So this is how we can manipulate the number of divisors, the sum of divisors. Whichever question we have, we can do it logically by first finding out the prime factorization correctly. If you mess that up, the rest of the problem will suffer, right? So first get the prime factorization correctly. Remember, it has to be all distinct prime numbers, and then just whichever condition is applied, make sure you're considering that correctly. For even, there has to be at least 1, 2. For divisibility by 4, there has to be at least 2 2s. So not divisible by 4, there cannot be 2 2s or more 2s, right? Even if we had 3 2s available and we added all 3, it would still be divisible by 4. So we needed to add less than 2 1s. For divisibility by 15, we needed to add 1 3 and 1 5. If instead of 15, we had, let's say, divisibility by 45, which is 3 raised to power 2 into 5. Then we needed to add at least 2 3s and at least 1 5. So like that, you can do any kind of conditions. I'm sure if you understood everything, the logic behind everything that we discussed today, you can solve all such problems very easily. Okay. Now, the number of ways in which 12 can be resolved into two factors. What is 12? 2 raised to power 2 into 3 raised to power 1. How many total number of divisors? Number of divisors is total number of divisors first, not the answer to the problem. Total number of divisors is 6. Thank you. 2 plus 1 into 1 plus 1. 3 into 2, 6. Even number of divisors, just divided by 2. So, 3 possible products, right? Also, not a perfect square, which is why we are getting 6. Why? Again, let's just verify. Why are we getting even number of divisors? Because there is 1, 2. Why do we have 1, 2? One even number here. Because here this was odd. This was odd. And because we had an odd power here, that means clearly this is not a perfect square. So, we can just divide it by 2. Which ones? 1 into 12, 2 into 6 and 3 into 4. Now, for 36 we have, clearly we know it's a perfect square, but let's just forget that for once and we start doing its prime factorization. Now this comes out to be 2 raised to power 2, 3 raised to power 2. All even. So yes, it's a perfect square. Total number of divisors is 2 plus 1, 2 plus 1, 3 into 3, 9. Odd, clearly it will be odd because even plus 1 odd, even plus 1 odd, we are multiplying only odd numbers, so we get a odd total number of divisors. Now we have to divide it by 2, not before adding 1 to that, right? Just like when we were doing it for 100, it was very similar, right? 2 raised to power 2, 5 raised to power 2, so just like that, we will add 1 and then divide it by 2. So 10 plus 2, 5. Which ones? 1, comma 36, 2, comma 18, 3, comma 12, 4, comma 9 and 6, comma 6. So 1, 2, 3, 4. 8 divisors we have here, and the 9th divisor, that was 6. We added one more 6 to complete the pair. Okay. So with this, we are done with this category of questions. Even though we just discussed one specific type of problems, but this was very important. This is very crucial to understanding. You will see a lot of applications here and there of this particular type. So we needed to discuss this separately and in great detail. But now I hope after today's class you can solve any such problem. You can use any of this in any problem. Even in our future classes, you will see that we will be using this information, this knowledge in other problems where we have something like this. We are checking how many cases can we make, how many possibilities are there of choosing out of these p identical objects, p plus 1. So like that we can use all of this. So make sure you revise all of this today, and I will see you in the next class. If there's any doubt, please go ahead and ask me. Otherwise, we'll end the class today earlier than usual, and we will continue the course in the next class. Yes. Okay, this is not a chemistry problem. Okay. So yeah, everything is clear. I'm pretty sure everything is clear. This was all very logical. So do not memorize any of this. Just all what you need to memorize is how we approached such problems. That should be in your memory, that oh, this is how we used to start such problems. We used to first prime factorize and then see how many prime numbers we need to select. Do not memorize the end formula. Memorize the approach, memorize the method. And with practice, you won't even need to memorize, it will just be in your memory. So keep practicing more and more. The more you practice, the more you will learn, the more you will understand. And I will see you in the next class. Okay, bye.